All right. Hey guys, as promised, I'm going to go through the problems on the review so you can see them. The first thing, and I already wrote these on here, but just to kind of show you what I added at the top of your review on the first page, these are the formulas we kind of used for linear equations. You should know these, so I won't have these on a formula sheet or anything, but the first one, if you're trying to find slope, remember find the change in y over the change in x, so y2 minus y1 over x2 minus x1, and then we've got point slope form here. You can use that once you know your slope. You can plug in m and then plug in a point for x1 and y1. Leave x and y just as x and y, but you can plug in the x1 and y1, and then if you solve that, sorry, I was trying to erase that, then you can get it to go to y equals mx plus b form. Okay, so to go through the linear equations, well, actually, since it's the beginning, I will show you then the exponential equations are here. So remember, we've got growth or decay, where a is the initial starting amount, and then 1 plus the rate of change to the t, and t stands for years. Or we've got y equals a, which is your starting amount, 1 minus r if it's decay, if it's going down, and t is your time in years. And then we've got our two different types of interest, compound interest. Remember, a is your amount, p is the principal, 1 plus r is your rate. Make sure you change your percent to a decimal, divided by n, which is the number of times it's being compounded, to the t times n. So same n, and then t is your number of years. Continuous interest is when we use E. Remember, that's a button on your calculator, but we'll kind of do one of those when we do the examples. Okay, so all of the answers are posted here in OneNote. If you just want to try these and then check your answers first. If you get something wrong, see if you can find your mistake. And if you still can't figure out, come watch this video and kind of watch me go through the problem. Okay, so go to our first one here. The first part's here is talking about the price of a particular model of car. It's $18,000 today, and the price is rising with time at a constant rate of $900 per year. How much will a new car of this model cost in 3.5 years? So since it's going up at a constant rate of $900 per year, that's our signal that this is a linear function. This is giving us this constant rate of $900 per year, so that is our slope, right? That piece. And then I know it started at my $18,000. This is my starting value, so this is my y-intercept. So I have those two things. I can just plug it in to get my function. To our y equals mx plus b. So y equals, my slope is 900 times x plus my b is 18,000. So there's our equation. If I want to know what the cost is going to be in 3.5 years, remember our slope here is $900 per year. So my x is what represents my years. So then to find my total cost, I'm going to do 900 times 3.5 plus my 18,500. And if I do 900 times 3.5, that gets us 3150 plus 18.5. And then add those, oops, we get y equals 21,650. So in 3.5 years, we'll have, or the car will be worth $21,650. Okay, ta-da, there's our first one. Okay, our next one. In 2010, the population of Boomtown was 1,650 people, and it began increasing at a rate of 250 people per year. Again, this one is very similar to the last one, right? It's giving us this rate of change. There's our slope. It gave us a starting amount, so there's our y-intercept. So then I can use those just to make my my function. So y equals my mx, my slope was 250. It is increasing. I'm going to pay attention to that. If it's increasing, I want a positive 250 here. If this was a decreasing, then I'd want to make that a negative 250. So make sure you pay attention to if our rate is an increasing or decreasing. Okay, so mx, so 250x, plus our y-intercept, or plus b, we started with 1,650 people. And our population's growing, right? Okay, so now I want to know what was the population in 2030. Remember our x here again, it was 250 per year, so that's our year. So I'm going to do Oh, shoot. Did I do this one wrong? I did. Okay, we got to start this one over. We'll fix that. And start again now. Okay, the next one says in 2010, the population of Boomtown was 1,650 people, and it began increasing at a rate of 250 people per year. Again, I see this rate of 250 people per year. So I know that's my slope. I've got that piece, right? This one's slightly different. The last one told us we started with an amount of 18,000, but this one is telling us that in 2010, we've got 1,600 or 1,650 people. So if you put those two together, that's like an X and a Y value. So we've got this point of 2010, 1,650, right? In that year, we had that many people. And then I know my slope. So in this one, I want to use my point slope form because I don't know the y-intercept. I just know a point on my line. So I'm going to use that y minus y1. So my y value in my point is 1650. And then let's give myself some more room here. I'm going to write it over here. So y minus 1650 equals my slope is 250 times x minus my x value of my point was 2010. Oops, just a 0. 2010. Okay, so then I can distribute the y or the 250. Y minus 1650 equals 250x, and then 250 times 2010. Whoops, that doesn't seem right. Let's try that again. 250 times 2010 would be negative 502,500. And then I'm going to add my 1650 over. So I'll get y equals 250x minus, if I add that, 500, 850. Okay, so now I've got my linear function there, right? There's my y equals mx plus b. So now if I want to know the population in 2030, that x represented the year it was, right? So I can do y equals 250 times 2030 minus 500, 850. And if we do the math there, we get 507, 500 minus 500, 850. So we get 6,650. And you can kind of look here to make sure your answer makes sense. We started in 2010 with 1,650 people, and now we're 20 years later, so we're going to expect that number to be bigger, right? So it makes sense that we got a larger number there. Ta-da. Okay. There are a couple other ways to set up this equation, by the way. So if you set up your equation differently, but you still ended up with the 6,650 people, don't worry about it. You still did it correctly. So there's some different ways you can treat the years there, but that's the easiest way I can see. Okay, on the back, same idea here. This time we've got your dog weighed 5.5 pounds at birth, and it weighed 20 pounds a year later, right? Based on these two data points. So there's my big hint that I'm going to make these into points, right? We want to find a linear function that describes how weight varies with age. Use this function to predict the weight at 5 years and 10 years, and then comment on the validity of the model. Okay, so we want to use weight varying with age, right? So I'm going to use age as my independent variable. So that means my first point here at birth, we'd be 0 years old, and our dog weighed 5.5 pounds. 1 year later, so at 1 year old, our dog weighed 20 pounds. Right, so now we've got our 2 points. Once I've got 2 points, I can create a linear function. First thing I need to do is find my slope. Right, so to find m, I'm going to do the change in y, so 20 minus 5.5. That's a big dog. It grew fast. And then 1 minus 0 on the bottom, change in x. So 20 minus our 5.5 is going to give us 14.5 over 1, which just means our slope is 14.5. And that's pounds per year, right? Because that's how much our dog gained in 1 year. Then we can use our same point slope form to come up with our equation. So I'm going to do y, or actually this one's even easier. This right here would be our starting value, right? Because at birth was our starting weight. So now that I know my slope, I can just write my function and do y equals, my slope is 14.5x, and then my starting value was the weight at birth, so plus 5.5. Right, that time we had to come up with the slope, but we already had the y-intercept. Okay, so we've got our linear function. If I then want to find my weight, or the weight of the dog in 5 years, my years is the x variable, so I'm going to do y equals 14.5 times 5 plus 5.5. And my weight in 10 years, I'm going to go ahead and set that one up too. I'm just going to plug in 10, right? Times 10 plus 5.5. Okay, so then if we calculate those, our first one, I'm going to get 78. And the second one, we get 150.5. Okay. Now remember that y variable is weight, right? So this is a 78-pound dog after 5 years and a 150-pound dog at 10 years. When it's asking, do you think this model is valid? I mean, you have to know a little bit about dogs, I guess, here, but if my dog was born at 5.5 pounds, a dog is usually full weight by the time they hit 1.5 to 2 years, I'd say. So the fact that my dog's going to keep gaining 20 pounds every single year doesn't make sense, right? A lot of dogs have a lifespan of only 10 to 15 years. So if I started a 5.5 pound puppy, I'm not going to end up with a 150-pound dog after 10 years. So I'd say no, it's not exactly valid because a dog is not going to gain the same amount of weight every single year. Eventually, they're going to top out at max weight. Dog won't gain 20 pounds every year. Okay. All right, our last one here for linear equations. It says the median age of men who married for the first time in 1970 was 23.2 years, and in 1998 it was 26.7 years. We want a linear equation to model this and then predict the median age that they will marry in 2025, and again, comment on the validity. Okay, so again, I see these kind of two groupings of data here. Those are going to be our 2 points, right? So in 1970, the age was 23.2 years, and in 1998, the age was 26.7 years. So again, we can use this to find our slope and then find our equation. So we'll start with our slope. And I'm going to do change in y, so 26.7 minus 23.2 over our years, 1998 minus 1970. So we get, make sure I get my numbers right here, 3.5 on the top, and 98 minus 70 would be 28 years, right? Because there's a decimal on top already, I'm going to go ahead and just divide that and make my slope a decimal, and that gives us 0.125 as our slope. You could, by the way, take those both by 2 and simplify the fraction. You get 1/8, but 0.125 is just fine. Okay, once I've got my slope, this time I don't know the y-intercept because neither of my x values are 0. So I'm going to use my point slope form like we did before. So y minus, I'm going to pick one of my 2 points. It doesn't matter which one I pick. I'm just going to pick the first one. So my y value was 23.2 equals my slope we had as 0.125. And then times x minus the point that goes with my 23.2 is 1970. Okay, so then I'm going to distribute, my slope, erase. So we get 0.125x, and then that times 1970 is 246.25. That's a negative. And then we're going to add over our 23.2. So we'll get y equals 0.125x, and then that plus 0.2 minus 223.05. Right? Okay, so now I can take my model. I want to find the median age in 2025. So I'm going to take my equation, y equals 0.125. For x, I'm going to plug in 2025, and then subtract 223.05. And then we just have to calculate that. So 2025 minus 223.05. We get y equals 30.075, right? And that, again, we're looking at years, so we could probably say approximately 30 years, right? So we're saying here the median age or the average age of men who married for the first time. And if we continue with this model, it's going to go to 30 years by 2025. We're actually kind of close to that year. I would again anticipate that this is going to go up, but eventually it has to stop, right? Like I would hope that eventually we're not going to have our median age for men getting married for the first time be all the way up at like 70 years old. So it's valid for a short amount of time, but not in a long term, right? So maybe we could say it's valid in the short term, but doesn't make sense over a long period of years. A lot of times we'll have linear models that make sense in the short term like that, but not if we keep going. So then maybe we have to look at a different type of model. Okay, so there's our linear equations. Basically, you just got to be able to pick out a slope or a y-intercept or points from the word problem, and then use your slope formula if you need to. Use your point slope formula, write an equation, plug in the values, and then be able to tell me if it makes sense or not. Okay, on to exponential. So this is the kind of second part we did here. Our first one, in 2000, the median home price in New York City was about $300,000. And from 2000 to 2006, our prices rose at an average rate of 11% per year. That rising at a rate of 1% per year is your hint, by the way, that it's an exponential. If prices had continued to rise at that rate, what would the median home price have been in 2017? Okay, so when we're doing our exponential model, we're always going to write, we've got our growth or decay, right? So we've got our starting price there of 300,000, and then the prices are rising. So we're going to use our growth model. So y equals, A is always our starting value, so our 300,000. And then I want 1 plus my rate. So we're rising by 11% per year, but remember you want to change that 11% to a decimal, so take and divide by 100. So that would be 0.11 to the t. Okay? And you could also, by the way, simplify that if you wanted to. This is totally fine. I would take that as a correct answer. You could also say it's 300,000 times 1.11 to the t, if you simplify it that way, or go ahead and add those two together. That's totally fine. Okay, so then if I want the median home price in 2017, now be careful here. Remember, this t over here is my number of years. So if I'm looking here, we started in 2000. That was our starting one. And now we want to know what's the price in 2017. So that's been 17 years. So I'm going to plug in 17 for my t. So y equals 300,000 times 1.11 to the 17th power. And so you're going to need your calculator for these, so make sure you've got one for your test. If I'm not there, I don't have a whole bunch to lend out to you or borrow one from somebody. Okay, so that to the 17th power. Make sure you do your exponent first. So 1.11 to the 17th first, and then times 300,000. So then we should get 1768527 0.81. So by 2017, that means our median home price is going up to 1.768527. The actual, so if I look at this part here, the actual median price of a home in New York City was 400,000. So why do we think that price drop or that price rise didn't keep going, right? Like, why is it so different? How is this only 400,000 when we predicted it was going to be that 1.7 million? There's several reasons this could have happened. We could just say that, maybe the housing market had a bad couple years and prices dropped. So housing market conditions can affect that rise in price. But basically, we can say that 11% rise didn't stay constant. It changed for some reason. And again, like we talked about before with the linear model, this model might fit well for several years. And then again, if that 11% per year changes in any way, it's going to change the price of the houses, right? So obviously this percentage decreased in this case if the price was actually 400,000. Okay, next one. Annual world oil production was 520 million tons in 1950. It increased at a rate of 7% per year from 1950 to 1972. So what was the world oil production in 1972? Right? Okay, so again, we are looking at an increase, right? So we're going to use our growth model again. So y equals, we want our starting amount in 1950 was 520 million tons. And then it increased at a rate of 7% per year up until 1972. So that's 1 plus, remember, change your 7% to a decimal, so 0.07 to the t is our model. And then if I want to find the actual production in 72, remember, you want to look at the number of years, because up here we started in 1950. So 1950 to 72, that's 22 years. So I'm going to do 520 times 1 plus 0.07 to the 22nd power. And I'm going to do my exponent to the 22nd times 520. And we get 2303.81. So that means that it's that many million tons is what that was measured in, right? Oil production. That's quite a big change. Okay, we continue here with that same problem on the next page. After 1972, the production growth rate slowed, right? So now our growth rate changed. So I'm going to use my answer from the previous problem. And now my growth rate is only 3% to see what the oil production might be in 2016. So now same idea, but we've got a different model, right? So we're starting in 1972. So that would be my answer up here from the previous problem, right? That's that, because we were doing 1972. So 2303.81. And now my growth rate is 3%. So 1 plus 0.03 to the t. Okay, so now if I want to predict, what did that mean about oil production in 2016? Well, from 1972 to 2016, that's 44 years. So we'll do 2303.81 times 1 plus 0.03 to the 44th power. And if we, whoops, wrong button, 1.03 to the 44th times 2303.81, we end up with 8458.33 million tons. Okay, so a little bit slower growth rate, but we get our two different answers with our two different models. So now it says world oil production actually reached about 4.8 billion tons per year in 2016. How does this compare to the value you found above? Okay, so careful here, because it might seem like this number is smaller, but this is actually 8,458 million. So if I do that, that's actually 8.5 billion tons. So we still got a little bit higher of a number, So again, it just means that our percentage rate was not quite 3% that whole time. At some point, that percentage rate changed, right? So again, we can just say the growth rate of 3% was not constant over all of those years. So less was produced. Right? Okay. We've got a couple more here. These are more just plugging into our formula, making sure we know how to do those. This is using our compound interest stuff. So Larry invested $27,000 in a savings account that pays an annual interest rate of 1.8%, compounded quarterly. Okay, so we've got our starting amount, we've got our interest rate, compounded quarterly, and we want to know after 5 years, right? So using our compound interest formula, we're going to do A equals, we're going to start with our principal, which is 27,000. And we're going to do times 1 plus our interest rate, which is 0.018, but we have to divide that by the number of times it's being compounded, which in this case, if it's quarterly, that's 4 times a year. And then times N, which is 4, times T, which is 5 years. And then we're just going to put that all in our calculator. Yours can probably do it faster than mine because you have better calculators. I got to do it one step at a time here. Let's do my exponent. Oops. Oh, I hit the button wrong. Okay, hold on. 0.018 divided by 4 plus 1. I'm going to do my exponent of 4 times 5, which is 20. And then times 27,000. And we should end up with 29,536.74. This is money, so I'm going to round to 2 decimal places. Right? That number should be bigger than what you started with. If you got a smaller number, you're doing something wrong in your calculator, right? Okay, next one. Jennifer is saving up for a house, wants to make a 20% down payment. She plans to purchase a house for $140,000. She has an investment account that pays 4.3% interest, compounded monthly. If she wants to buy the house in 5 years, how much principal does she need to put in her account to have the down payment ready? Right? Okay, so there's a couple things going on here. The total price of our house here is $140,000. She wants to make a 20% down payment. So first thing we need to do is figure out what that down payment is, right? So our 20% down payment is going to be 20% of $140,000. So I'm going to do $140,000. Take that times 0.2 or 20%, and we get $28,000. Right? So that's the amount of money that we want to end up with, right? Okay, so now I have an investment account. We pay this much interest, compounded monthly. We want to buy in 5 years. We want to know how much do I have to start with, right? This is what I'm looking for. I want to end up with my 28,000. So we're plugging things in a little bit differently to our equation. So I want my 28,000 to be what I end up with. So that's what I equal. The principal in my account is what I don't know. So P is what I'm going to solve for. And then the rest of this part is the same way. So 1 plus my interest rate is 4.3, so 0.043 compounded monthly. So that's 12 times a year. And then again, I get 12 times my 5 years, right? Okay, so I can calculate all of this stuff over here first. Right, so I can do my 0.043 divided by 12. I'm going to add 1. And then I'm going to do that to the 12 times 5, or the 60th power. So then we get 28,000 equals P times, and I'm going to give a couple decimal places here, 1.2394. So then I just have to divide both sides by my 1.2394. So 28,000 divided by my 1.2394, and we get 22,591.86. 50, if I round up, 58 equals P. Right, now this time we should expect this number to be smaller than our 28,000, which it is, because this is how much I need to start with so that I can end up with that down payment of $28,000. Okay. Okay, so same formula, but you're solving for a different variable there. Okay, then our last one, Marcus purchased a new car. Average depreciation rate is about 19%. Assuming this, how much will his car be worth after 6 years? Okay, so depreciation means our value is going down, right? So this time we're looking at exponential decay. There's no interest here, so I'm not doing compound interest, but my amount is going down. So I'm going to start with, oops, wrong one. Sorry, we did y equals 46,500 times 1. And this time I'm going to subtract because it's depreciation. Do my rate of 0.19 because that's 19% to the t, which in this case is 6 years. So then I'll do my 1 minus 0.19, raise that to the 6th power, and then multiply by 46,500. And that gives me 13,132.97. So that's how much that car would be worth after 6 years. Cars depreciate fast, right? Okay, so got a couple different things there with exponential. So being able to write your exponential model with either growth or decay, and then your compound interest formula, being able to use that to calculate some things. That's what you got to know. I will give you these formulas, the exponential ones, on the test, so you'll have those. You don't have to memorize them. The linear ones you should know. I'm not going to give you those, so make sure you know your slope and point slope for them and how to do those. But I will make sure you've got the compound interest in those formulas because you'll get given those on the final as well. Okay, feel free to send me messages on Google Chat if you guys have questions. I'll be in and out of sessions at a conference, but I can try my best to reply to you as quick as I can if you guys have questions. And actually, when you're in class, I'll probably be on a plane, but I will be around in the afternoon if you have questions or in the evening. Okay, have a good one.